piano is not in tune. Did you guys know this?
No, not really, until this week. Hi David, you sent me a wonderful video last week about how and why the guitar is tuned and its relationship to the pentatonic scale. So I decided to uncover the secret behind the piano's tuning and uncover the mystery of why Jacob Collier is always talking about how the piano is out of tune. Like, what does that even mean? Let's dive in. The answer has to do with harmonics and a little bit of math. So I know you know about this thing called the harmonic series, and this idea that we hear a note at a specific frequency, and accompanying that note, our ears like to hear integer multiples of that frequency accompanying that note. That creates intervals that sound really nice to our ears. So I have this chart here which shows a fundamental frequency and all of the multiples of it. And these are the intervals that we know of as musicians. So if you take a fundamental frequency and you multiply it by 2, you go up an octave. That's what we hear as an octave. If you go from this second one to this third one, which is you're taking the fundamental frequency times 2, and then you're multiplying it by 3/2 to get to 3 times the fundamental frequency. That is the equivalent of going up a fifth. From the third to the fourth, that's going up a fourth, etc. So these represent the sort of perfect harmonics intervals where they're tuned so that they're at these perfect integer multiples of the base frequency. So when Jacob Collier says perfectly in tune, he's talking about being perfectly in tune in the sense that we are playing harmonics. We are using these nice simple ratios between our intervals. Great! Now with that in mind, let's design an instrument, the piano, where all of these intervals are our nice, beautiful harmonics intervals that we love, that sound so nice to our ears. Say I'm starting with C here, and I'm going to tune sort of relative to that C. As we discussed with our ratios from before, if I want to go up, say, a major third using that harmonic, I am going to be multiplying the frequency of this base frequency by 5/4 to get to a major third up. A major third is also 1, 2, 3, 4 half steps. So this interval, going from here to here, I'm multiplying whatever this frequency is by 5/4. Awesome. Great. To get from here to another major third, I'm also going to multiply by 5/4. And then to get from here to here, I'm also going to multiply by 5/4. So in the end, the calculation I'm doing is 5/4 times 5/4 times 5/4, 5/4 cubed. Okay, here's the problem. From here to here, that's an octave. I want, if I'm going to be in accordance with these harmonics, this frequency to be 2 times this frequency. Here's the problem. Right now we've just defined it if we're tuning by thirds, if we're stacking 3 major thirds on top of each other. If we stack 3 major thirds in the harmonic sense, 5/4 on top of each other, we get 5/4 cubed, which is 1.953125. That is not 2. So we've just shown that when we tune things by the major third according to the harmonics, we're actually going to be slightly out of tune in other areas. So there's not a way to make this consistent with each other. There's not a way to make the major thirds consistent with the octaves in this tuning. Great, so it's impossible to tune a piano in accordance with these harmonics. So how is the piano actually tuned? Well, here's what we came up with. We start with C, and for every half step, we're going to multiply that frequency by the 12th root of 2. That might seem really weird. It's an irrational number. It is not a nice ratio like our other ratios were before, but we're just going to multiply each one by the 12th root of 2 each time over and over. It actually kind of does make sense because if we multiply by the 12th root of 2 12 times, we're going to get 2. So actually from C to C, or from any octave on the piano, that is perfectly tuned. But we suffer a slight consequence, because let's look at the perfect fifth. So that's going to be the 12th root of 2, 1, 2, 3, 4, 5, 6, 7 times. The 12th root of 2 to the 7th is 1.498, which is slightly less than 3/2, which is the ratio that we wanted before from the harmonics. Similar with the perfect fourth, which is 1, 2, 3, 4, 5. That's also going to be slightly off from the true perfect fourth. So we have this compromise which lets all of our keys sort of be in tune in the same way, but all slightly out of tune with our harmonics. The differences between some of these intervals are so significant that you can actually hear how out of tune the piano's intervals are with the harmonic intervals.
This is this one, and then if I sing. That's how out of tune the piano is.
Tuning a piano like this has its advantages and its disadvantages. On the plus side, there's a standard system, every key is in tune in the same way. On the downside, we kind of lose that magic of those harmonic intervals by making sure that all of the semitones have to be exactly equally spaced apart. It makes a lot more sense to me why Jacob Collier would go to so much trouble to like change the tuning on his like Logic sessions of different like notes on the piano and not just like record straight from an acoustic piano, because the major third in like Tune to the Harmonic series like sounds so good.
If you look at the world and you look at your life, it's wonky. Life does not do that, right? Life does this. Yeah? So music for me is very important that you also let music do that if it needs to. And in a similar way to actually the piano is not in tune. Did you guys know this? Yeah? Oh, that's great. So